all. Today we'll be discussing about the one topic. It is related to the capacitance of two single phase transmission line. So transmission line, what is transmission line? Transmission lines. So transmission lines are the overhead line, as you know, overhead line. So as of now, you don't have that much knowledge on transmission line, but whenever you will be studying power system, then obviously you have to study the lines, transmission lines. Okay. So transmission lines are basically single phase and three phase line. So in case of single phase line means one line with neutral, you can see, and in three phase line, three phase will be there. Okay. So in practical case, so these are the line, single phase line and three phase line. Okay, overhead line. In your locality, you can see that overhead lines are coming from generating structure to customer. Okay, not only exactly customer. So from generating station to it's coming to substation, and from substation is coming to our households. Okay. So its main purpose of this transmission line to transport the power. Okay, as we know all. So transmission lines means this type of conductor. Okay. Conductor carries the power. Okay, from generation to customer end. Okay. Now the towers, you can see that some lines you will see that 6 phase are carrying. Some lines you will see the 6 phase. 6 conductor you will see, and above all you can see a thick wire. So that thick wire is known as the earthing wire, and other 6 lines, and 3 of will be one 3 phase line, and another 3 will be one 3 phase line. There is a combination of double circuit line. Okay, this is known as the double circuit line. But only if you see that 3 phase are there, and above all one thick wire is there, that is earthing wire. So that is on single phase, single circuit, 3 phase line, and one will be the single phase line. Okay. So for this line calculation, we have to go for the performance of the lines. Okay. So to study the performance of lines, so we have to see, we will see. So there have some, we have to see the parameters of line. So parameters of line, in the parameters of line, so you will see the series parameter is inductance, resistance. Okay, it may be distributed or it may be lamped. It may be distributed. This L also may be in distributed nature or in lamp. But for our presentation, we will study for and one more thing we can add. I want to add with this. So transmission lines are basically three types of line. One is long transmission line, long TL, medium TL, and low short TL, short transmission line. Okay, this transmission line is basically depends on the frequency. Okay, so we will decide the frequency and the distance and the length of the line. Okay, it is depend on frequency and the length of the line. Okay, suppose source here to substation. So this is the length of the transmission line. Okay. Now, what are the parameters? Parameters are the first one is the series parameters are resistance, reactance, and the shunt combination of conductance and capacitance. Okay. So in case of shunt combination, so there we will see that capacitance with this we simply can consider the conductance. Okay. Capacitance and conductance. Okay. So that's why we have to study the capacitance for the calculation of performance of the line. Okay. So that's why we have to calculate the capacitance for two-wire line. Okay. Also, and later on, whenever you will study, then you will calculate. You have to study. You have to calculate. You have to know about the calculation procedure of double circuit line and three-phase line, single circuit line. Okay. So, but here in this course, we will be studying only a single phase line. Okay. That means two wire transmission line. Okay. So, before going to study the two-wire transmission line, transmission line, capacitance is a what? Shunt type parameter. Okay. So we have to know about such these things. First we have to know about the electric field intensity due to an infinite line charge. That means for the line distribution, what will be the electric field intensity? Already we have discussed. Okay. And two, what? For this electric field intensity, if there are 2 points are there, any 2 points are there, okay. So what will be the potential difference between 2 points, between 2 points in that electric field. So here we are discussing about the free space, the transmission line. So obviously there will be a free space consideration. So epsilon only. Okay. There will be the no dielectric medium, yes, such things. Okay. Only free space consideration will be here. Okay. So firstly, see the condition. So now for rho L for line distribution, okay, minus plus rho L. So for this any point P, so what will be the electric field intensity for this? What will be the electric field? This is R. So electric field, as you know, the E. This is the radial distance from this to this. Okay. So rho L 2 pi epsilon naught R, the direction of R. So automatically it's what is presenting the spherical coordinate system. Remember it, okay? It's presenting the spherical coordinate system. Clear? Now any point this point, suppose somewhere here and here, suppose here from this point, okay, just more clear to do, more clear about this than what suppose z-axis, z-axis. So suppose along this z-axis, OL is there. Okay. So anywhere, suppose here R1, R2. Okay. So for this and this way and this. Okay. At this point and this point. Okay. So what will be the potential difference between this to this? Potential difference between this to this. So as we know, the potential minus final to initial. Okay. E into EL. So for this DL, elementary line element will be for this case DR, AR, DR, AR cap. Okay. So E into DL. Okay, here E is what? E is rho L by 2 pi epsilon R dr. So now what will be the potential difference? Potential difference will be minus R2, R equal to R2, R1. So this R rho L 2 pi epsilon naught R dr into dr AR. Clear? So now what will be getting? From there will be getting this rho L 2 pi epsilon naught ln R2 by R1. So remember these things. We will be utilizing many more times in this equation. Okay. So now one more thing we have to discuss for the two transmission lines of charge. Okay. So now so maybe the configuration will be like this. Okay. Suppose here one transmission line, N transmission line. Okay. Just simply I am just before going to discuss clear about this. So I just want to clear. Suppose here maybe some conductor radius will be there. Okay. And here the radius of the conductor we can consider. But there will be the spacing between two conductor, center to center. Okay. So maybe this is the cylindrical type. So there will be some conductor. Suppose this is R. This is very small. Okay. And this the spacing will be much more for transmission line. Spacing between two conductor is much more greater than the radius of the conductor. Obviously, this is the practical part. Okay, practical thing. Okay. So now, if you study about this, the conductor with two infinite long charge. Okay, with different polarity. Okay. Suppose here it is negative polarity and suppose here it is positive polarity. Okay. These are the long charge and these are the spaced in where? In suppose this is distributed along z axis. This is also distributed along z axis. Clear? So now somewhere suppose we are considering the origin. origin. Suppose here somewhere we can consider as origin. Okay, this is the x-axis. We can consider this is x-axis, y, this is z-axis. Okay, so along z-axis these are, so this rho L is nothing but what? XY plane. Here also XY plane. Okay. Now somewhere this point where the XY plane, this charge distribution is intersecting. So this point is what? Will be sub x will be 0, y will be somewhat what? Suppose from this to this distance is s in positive direction. So obviously here also and s. We are considering this. These are with respect to the origin. This is the origin. Okay, with respect to, they are symmetrically positioned, located. Okay, so that means here what we can see. So from the method of images we studied. So for this rho L and this rho L at this along this z axis, what will be the velocity potential? Potential will be V equal to 0. That means this is the equipotential throughout. This z axis will be the equipotential into this and this. Clear? So now we can consider any point. So here and here. Okay. So from this to this we can consider for this point what? 0, s, minus s and 0. For this 0, s, 0. Clear? So distance between z axis to where the located this line distribution is there, the distance is s. Clear? Now somewhere any point on this plane. Okay, suppose we are considering this plane. This is the xy plane. Okay, suppose this plane somewhere any point. Okay, we have to calculate z obviously will be 0. We have to calculate the potential. Okay, due to this and this. Clear? So due to this, what? Suppose up to this point, you can, this is R2. Okay, for this you can consider this is the radial distance R1. Okay, clear? So and from origin to this, suppose some distance. Okay. Now what will be the potential at this point? Okay, on xy plane. Suppose P is a point. P is a point on xy plane. So obviously P will be x, y, 0. Okay, as we discussed in the method of images. Okay, so this thing should be okay. So now the potential for this at P, what will be the potential? Total potential due to V plus and due to V minus. V minus due to minus rho L. Okay, and V plus due to plus rho L. Okay, now we'll see what is the V plus and V minus. So V plus will be what? V plus will be nothing but rho L, that means rho L 2 pi epsilon naught 1 by R. Okay, R equal to S to R equal to R to dr. These things we will be getting. Okay, so finally we will be getting what? Rho L 2 pi epsilon naught 2 pi epsilon naught ln S by R2. Okay, these things we will be getting. Okay, and for in similar way V minus we will be getting minus rho L 2 pi epsilon naught rho L S by R1. Okay, so now total potential we will be getting V plus V minus we will be getting as rho L 2 pi epsilon naught ln R1 by R. This expression. Remember these things. This will be utilizing. Okay. So, what is the similar thing for single charge line? For single charge, this line, this equation. So, let's take this equation and the equation number 2, and that one before we start discuss. This one we can consider as 1. Okay. So this equation is what? The for due to rho L means one positive rho L due to that electric field intensity. If anywhere we move one point to another point, so whatever the work done is there, so that is representing this potential. But for here two potential, now two bipolar electric field line distributed charge available, they are symmetrically positioned. Okay, so now that potential for this is the same, expression is same. Okay, so you have to remember this R1 and R2. R1 as calculated from the position of this conductor and position of this conductor. So this position to that particular position P, and from this position to particular position is the radial distance. Okay, so perpendicular direct distance. Okay, so what is the now what we can see from this equation? This is the potential equation. Now see this rho L for a configuration, rho L is a constant, 2 pi naught, this is also constant. Now the V ln R by R2. So R1 by R2, if we take as a constant, suppose any constant, okay, it must be a positive constant, obviously. Clear? So now see, if this constant is K, so simply we can say that this potential will be the same potential. So then if it is constant, then obviously this also will be constant. So if this happen, then what will be? Then this happen means this the constant potential line will be getting. We will be getting what? Constant potential line. Constant potential line. Potential lines. That means what? The equipotential lines. Equipotential lines will be getting. Clear? So now equipotential lines will be getting. So now what we will be saying? We will be finding the locus of the equipotential line. Locus of the equipotential line. So what will be the locus of the equipotential line? So what will be the locus of the equipotential line? So see. So this is somewhere this point. Okay. Now we can consider with this R. Okay. R and this is R. Suppose we are taking somewhere here R. Somewhere here one point we are taking. Okay. With respect to any point, any point. So with respect to that point, suppose we can consider make a circle. This R. Okay. So R we can make a circle. So with this R1 and this is R2. So see here what will be the R1. Here also we can make one circle with this radius. Suppose with this R1. This is R1. Just it's not clear looking, but we take as a circle with radius R1. And for this also R2. Here also we will be taking one circle. Okay, that is R2. Clear? R1 and R2. So now from that equation position of this, so R1 will be what? R1 will be the what will be the R1? Distance between this and this. So P is x, y, 0 and this rho L 0 minus S 0. Okay. So R1 is between this what? Distance between x 0 and 0 minus S 0. So what will be the distance? S square plus y plus square equal to this R1. So for R2 will be the x square plus y minus a square. Clear? So this what we got the potential equation. Potential equation is the rho L 2 pi epsilon naught ln R1 by R2. Okay. So this K is R1 by R2. Clear? So R1 is under root S square plus 2ys plus y square, but it is plus x square, and R2 is s square minus 2ys plus y square plus x square. Okay. Now this K is any constant. If this is any constant, then what? We can square it. This K square. Okay. Y square plus 2ys plus x square plus x square. Y square plus minus 2ys plus x square plus x square. Now if we do the operation, this operation k square plus 1 square minus 1. So this operation if we do, then what will be getting? This is getting 2 into y square s square plus x square. In the numerator term, in the denominator term, we will be getting 2ys. Okay, 2ys. So these two will be getting cancelled. Now, what will be getting? This is x square plus y square plus 2ys k square plus 1 k square minus 1 plus s square equal to 0. Sorry, it will be minus. Okay. X square plus y square. So now, if this equation we take as a reference of this, from this is the x under equation from the circle, x square plus 2y square minus 2gx minus 2hx minus 3y plus c equal to 0. By comparing this is the this equation is a circle equation. Comparing this and this, what will be getting? So we will be getting the radius. Radius is how much? The radius is 2ks divided by k square minus 1. So this radius what? This radius is nothing but the equipotential lines. So if radius, so throughout this path the potential will be same. Okay, potential will be same. Clear? And here what will be the y? Y is nothing but g. G is k square plus 1 k square minus 1 into s. These things. Okay. But x h equal to 0. This thing will be getting. So as from this discussion, above discussion, and the equipotential line corresponding to the voltage at V at P, at the total potential V at P, what? The higher potentials, that means if K increases, also potential will increase. From the equation, you know, if K increases, the potential also increase. Okay. It can be seen from the equation of the equipotential line. If R decreases, suppose this is the small r. If suppose small r, so this r is what? This radius we are considering the small r. This radius we are considering the small r. Okay. So here there is a transmission line. So here some with this point, this r we have considered. Okay. So this r1 to give the potential equipotential line. Okay. So here the potential will be same. Okay, with this R, small r. So this R is nothing but what? R is nothing but 2 Ks K square minus 1. Okay, this. So if R decreases, suppose if R decreases, then what? That means suppose R decreases, that means R tending to 0. R tending to 0, that means the conductor का जो radius होगा, radius of the conductor is shrinking. Suppose it's tending to 0, that means that means G tending to S, so that the equipotentials are smaller circles, with their centers more nearly at the line of charge. So again you see this line. Okay, again I am repeating this. With these conditions, this G, if R tending to 0, then G tending to S. Okay, G tending to S, from that so that the equipotentials are smaller circles with their center more nearly at the line charge. That means what? अभी यहाँ पे जो देखे हैं हम लोग, ये तो पॉजिटिव चार्ज का सेंटर था, यहाँ पे कुछ सम आर रेडियस का था, ठीक, यहाँ पे कुछ रेडियस था, सपोज यहाँ पे कुछ रेडियस बना था, इंटरसेक्ट किया, ठीक, ये आपका आर था, ठीक। तो अभी अगर आर खूब छोटा हो जाएगा, ठीक है, तो जी टेंडिंग टू क्या है, ये आपका क्या एस के बराबर होगा। तो अभी यहाँ पे इसके जो बराबर होगा, ये जो होगा बराबर, ठीक है, with their center are more nearly at the line charge. तो ये जो सेंटर होगा, ये सेंटर तब यहाँ पे ऑलमोस्ट शिफ्ट, ठीक है। यहाँ पे जो सेंटर एक आर्बिट्ररी सेंटर बनाया, वो एक सेंटर यहाँ पे ऑलमोस्ट जो यहाँ पे रो एल था, पॉजिटिव रो एल, वो यहाँ पे शिफ्ट, ठीक है। तो इसका मीनिंग क्या है, जब रो एल बराबर जितना आपका पोटेंशियल आर, रो एल आपका जो होगा चार्ज, जो कंडक्टर का होगा, कंडक्टर का जो रेडियस होगा, ठीक है, अगर इसको छोटा कर देंगे तो इसके बराबर आपका इक्विपोटेंशियल आपका रीजन मिलेगा, इक्विपोटेंशियल, yes, voltage equal to constant, some constant, so voltage across this some potential will be there, equipotential.